In the course of doing chemistry, we are definitely going to be performing some chemical reactions. Our notation for representing these chemical reactions is we're going to write the substances that we start off with, and plus signs indicate that they are all being added together. Then we are going to write the substances that we wind up with at the end of our reaction, and a forward arrow indicates that we are progressing from the substances on the left into the substances on the right. Our starting substances, those are called reactants, and our final substances are called products. You can almost think of this as a mathematical equation. This arrow is the equal sign in that equation, and what it's stating to be equal is the mass that we begin with and the mass that we wind up with. So that's our law of conservation of mass. Now we can make an improvement here because we know the formulas for hydrogen and oxygen and water using our notation. So we could write that H2 gets added to O2 to become H2O. Now we've written the exact same thing, but we've represented our knowledge about the molecules that make up these substances. Remember that nonmetals tend to form diatomic gases, gases with two atoms attached to each other. So that's why we have our H2 and our O2, and we get our H2O. Now, I think there's a slight problem here. The problem is not too big a deal. We've just violated all the fundamental laws of chemistry, including Dalton's atomic theory. What do? We destroyed an atom here. Dalton says we can't do that. We had two oxygen atoms on the left side, and we had one oxygen atom on the right side. Well, the problem here is that we've introduced our notation which represents the exact quantity of atoms involved in this reaction. What we forgot to do was to introduce a notation to represent the quantities of molecules involved in this reaction. To improve our notation, what we are going to do is write what's called a balanced chemical equation. Balanced because we have the same quantities of atoms and same amount of mass on the left side as we do on the right side. Now our problem was that we had two oxygen atoms on the left side and only one oxygen atom on the right side. The way to fix that is pretty straightforward. Just double the amount of water molecules on the left side here. And now we have all the oxygens that we need. This is okay because remember in our laboratory, we just had a bulk quantity of hydrogen and a bulk quantity of oxygen and added it together and got a bulk quantity of water. So we lied when we introduced these numbers of atoms here. And what we're doing now is we're fixing the lie. We're making it match the situation more accurately. But this is usually the case. You solve one problem, you create another worse problem. Right, now we have the right number of oxygens, but we have the incorrect number of hydrogen atoms. We have 4 on the right, and we only have 2 on the left. Let's trudge ahead anyway. Let's try the same technique in order to fix our hydrogen atom problem. Now we have 1, 2, 3, 4 hydrogen atoms, and we have 1, 2, 3, 4 hydrogen atoms. So we've solved the problem. We have the right number of hydrogen atoms, we have the right number of oxygen atoms. Now to indicate this change in our equation, what we do is we put coefficients in front of the molecules. And these coefficients tell us how many moles of molecules are involved. So we need to have a 2 to represent these 2 water molecules, and we need to have another 2 to represent these 2 hydrogen molecules. And what this is saying is that if we take 2 moles of hydrogen and we react them with 1 mole of oxygen, that we'll get a total quantity of 2 moles of water in return. And these coefficients that we've written have a complicated name. They're called stoichiometric coefficients. But all they are is just numbers which modify the ratio of the molecules involved in the reaction. These are the steps that we're going to follow to write our balanced chemical reactions. First thing we need to do is we need to write whatever equation we can come up with. It's probably going to be unbalanced. The important feature is that it includes all of the substances. Our whole balancing process relies on counting the number of atoms on the left, the number of atoms on the right, making sure they match. If we've forgotten any molecules, it's not going to work. And so we just need to write down our reactants on the left and all of our products on the right. We should be good to go on to the next step. Next, we're going to go ahead and adjust the coefficients. Not the subscripts. You can't change the quantity of atoms in a molecule. You can only change the number of molecules, which is represented by those initial coefficients. And you're going to adjust those coefficients to balance the number of atoms of each type. Have to have the same number of carbons, the same number of oxygens, the same number of hydrogens, etc. And our last step is that we're going to go ahead and simplify this. So if we introduce any fractions, which we're allowed to do in the balancing if we want, we're now going to eliminate them by multiplying by whatever we have to make them into regular numbers. We're also going to divide out common factors. So if we have 2 H2s becomes 4 H's, then 2 and 4 are both divisible by 2, so we would go ahead and divide by 2 and make the equation more simplified. We're in our laboratory and we do an experiment. We take some powdered sulfur and some fluorine gas and we let it react. We do some analysis on the product and find that we have created sulfur trifluoride. Now what we would like to do is we would like to represent this all using a reaction that shows what the molecules themselves are doing. So the first thing we're going to need to do is just get it all on paper. So we just need to write down the fact that we have solid sulfur and that we have fluorine gas. Remember those nonmetals, they form diatomic gases with 2 atoms attached to each other. And our product was the sulfur trifluoride. Now this is fine, but we have a bit of an untruth here. Our untruth is that our reaction states that there are 3 fluorine atoms that we wind up with, but only 2 fluorine atoms that we started with. And John Dalton says, no to that. We can never create or destroy elements. If they're there in the end, they're there in the beginning, and vice versa. So the way we're going to fix that is we need to adjust the number of molecules in our equation. Now let's do a trick here. What we're going to do is we're going to multiply by 3 over 2. So 3 divided by 2 times 2 is 3. So we now have 3 fluorine atoms on the left side, and we have 3 fluorine atoms on the right side. We also need to make sure that sulfur matches up, but we already have 1 sulfur here and 1 sulfur there. So we're good on sulfur. Now, unfortunately, we can't physically do this. We can't actually take our fluorine molecule and chop it in half so that we only have an extra half fluorine. What we're going to need to do instead is we're going to need to double all of these quantities. So as part of our simplification step, we get rid of any fractional or decimal numbers. Could have also written this as 1.5 here. So to fix that, I can just multiply the whole thing by 2. And this behaves very similarly to an actual mathematical equation. So we want this half to go away, so we multiply that term by 2. But if we do that, since it's an equation, we have to do the same thing to everything else. So we have to stick our 2 in front of the sulfur and our 2 in front of the sulfur trifluoride. And if we count up all of our atoms now, we'll find that we have 6 fluorine atoms on the left, 6 fluorine atoms on the right, 2 sulfur atoms on the left, 2 sulfur atoms on the right. So we have successfully written down a balanced chemical equation. Something very powerful that we can do, having come up with these balanced chemical equations, is we can use them to convert between the amount of one substance we have into the amount of another substance that we have over the course of the reaction. This is called stoichiometry, since we're using those stoichiometric coefficients to do it. And so as an example, let's say we have this reaction. What this reaction is saying, if we have 2 molecules of A and a molecule of B, we will get 3 molecules of C. And we often talk about moles, since we usually have a lot more than just a single or a couple molecules. So we often think of this as 2 moles worth of A molecules plus 1 mole of B molecules will yield 3 moles of C molecules. So what that's saying is that we have a 2 to 3 ratio of moles of A and moles of C, and we can throw that into our dimensional analysis to our factor label equations in order to convert between A and C if we have information about one and want to obtain information about the other. And the way we do that, so first we have to write and balance chemical equation. Balancing is absolutely essential. This will be a case of garbage in, garbage out if you don't balance. You'll get a useless answer and you will have wasted all the time that you spent after step 1. Now, we don't actually have molecule counters in our laboratory. What we do have is we have scales that can measure mass. So our laboratory information is going to be referring to mass. But this equation, we cannot use it for mass. It only refers to moles. So we're going to have to convert from mass into moles to use our handy dandy trick. And once we have done that and done our calculation, then we can convert back into mass. So we'll do that. We'll use the ratio to get from the moles of the substance that we know about into moles of the substance that we're inquiring about. And now again, once we are confirming the results of our experiment by seeing how much of this substance we actually did get, we're not going to be able to use a molecule counter. We're going to have to use a mass balance or scale in order to do that. And so our final step is going to be to convert back from moles into mass. Suppose we do a reaction between hydrogen and nitrogen. We combine them together and we find that it produces 3.1 grams of ammonia. Well, if we know that, then how much hydrogen do we suppose was involved in this reaction in order to produce that ammonia? This is the kind of question we can answer using our stoichiometry, which allows us to convert information we have about quantities of substances into information about quantities of other substances. Now, in order to do our stoichiometry, we are definitely going to need a balanced equation. So we know we have hydrogen, we know we have nitrogen, and we know we wind up with ammonia. Well, we have 2 atoms of nitrogen on the left, and we have 1 atom on the right. So let's go ahead and fix that by doubling the amount of nitrogen we have on the right side. Okay, now we have 6 atoms of hydrogen on the right, and we have 2 atoms of hydrogen on the left. So we can fix that by stipulating that we have 3 hydrogen molecules instead of just 1 hydrogen molecule. And now we should have 3 times 2 is 6 hydrogen atoms, 2 times 3 is 6 hydrogen atoms. So this is our balanced equation. Now that we have our balanced chemical equation, it's time to convert into moles so that we can actually use it, since chemical equations only describe relationships between moles. Well, the first thing we need to do, since we have a mass, we need to find the molecular weight. Now that we have a balanced chemical equation, what we're going to want to do is we're going to want to convert our mass into moles, because chemical equations describe mole relationships, so we can only use them once we have done this conversion. Our first step is that we're going to need to know the molecular weight of our ammonia, our NH3, since that's what we have the mass of. So to find the molecular weight of NH3, we can use our law of conservation of mass. We just have to add up the mass from the nitrogen and the mass from the 3 hydrogens, and that total should give us the molecular weight of the NH3. And these masses we just look up in the periodic table. Now, having done that, we can now use dimensional analysis to get from our grams that we don't want into our moles that we do. Now, because we want grams to cancel out, when we use this ratio that we've come up with, the molecular weight of NH3, we're going to want to put grams on the bottom. So we put the 17.03 grams on the bottom and the 1 mole on the top. So now grams of NH3 should cancel, and we multiply and divide all these numbers, and we get 1.82 moles of NH3. And I've kept an extra sig fig here, even though this should only have 2, just so that I don't lose too much accuracy due to rounding errors. But at the end, I'll square all my sig figs and make sure that I give my answer to the proper decimal. Now we have our balanced reaction. We have our quantity of moles of NH3. We're ready to do some stoichiometry and convert our information about NH3 into information about N2, the other substance in the reaction. So we're going to need to use our equation to get the coefficient that we need. So we see that for every 3 H2 molecules involved in the reaction, 2 NH3 molecules are also involved. So let's take our 0.182 moles of NH3 that we calculated and multiply it by 3 H2s for every 2 NH3s. You can think of this as canceling out as a unit. So the NH3 goes away, and now we've gone from moles of NH3 into moles of H2. So we multiply 0.182 by 3 halves, and we get 0.273 moles of H2. Now our final step, we figured out how much O2 we have in moles, and we wanted to know how much O2 we have, but unfortunately counting the number of O2 molecules is not very useful in the laboratory. We need to relate it back to what we can actually measure in the lab, which is mass. So our final step is another piece of dimensional analysis. Go ahead and convert from moles into grams. We take our 0.273 moles of H2 that we calculated, and if we add together 1.01 grams per mole for each of these hydrogen atoms that we look up in the periodic table, and we'll get 2.02 grams for H2 for every mole of H2 molecules. And so moles cancels, and we are left with grams of H2. And you get 0.551 grams of H2 product. Or sorry, it was an H2 reactant that we used to produce that ammonia.